back everyone. In today's lecture we are diving into adversarial search or game playing search. This is one of the most exciting parts of AI because it connects intelligence with games like chess, backgammon and poker. These games are competitive, they involve strategy and they push AI to make smart decisions under pressure. Let's get started. Okay. Move ordering. The effectiveness of alpha beta pruning is highly dependent on the order in which the states are examined. Do you know what it means? First, okay, first go through this slide. Like, we could not prune any successor of D at all because the worst successor from the point of min were generated first. If the third successor of D had been generated first, we would have been able to prune the other 2B. If this can be done, then alpha beta needs to examine only big of B power m by 2 nodes to pick the best move instead of big of B power m for min-max. This means that the effective branching factor becomes root of B instead of B for chess, about 6 instead of 35. Due to this, alpha beta can solve a tree roughly twice as deep as min-max in the same amount of time. If successors are examined in random order rather than best first, the total number of nodes examined will be roughly big of B power 3m by n for moderate B. Okay, let me explain this to you. First, let's talk about move ordering. Okay. The effectiveness of the famous alpha beta pruning algorithm depends on a lot of order in which we examine states. Like we know 2 power n, this is an order of n, 3 power n, like 2 power n into 2. Okay, in which order? Like, see, B is B times, B power m is B power n times, B power m by 2 means B power m by 2 times, like 2 power 2, for example, let's say 2, it means 2 times. Okay, we are going through it 2 times. If you say 2 power n, it means 2 into n times, like 2. It's like, for example, 2 power 2, that's 2 into 2, 4 times. It multiplies exponentially. See, this is exponent, right? So it multiplies exponentially. So the effectiveness of the famous alpha beta pruning algorithm depends a lot on the order in which we examine states. For example, if we are exploring the successors of a node D and we fortunately start with the worst moves, like like directly we started from the worst. Okay, then pruning doesn't really help. We have to examine almost everything. Okay, but if we start with the best moves, pruning kicks in early and we can cut down a huge portion of the search tree. For example, let's say we want to there is a basket full of balls or tomatoes, let's say tomatoes. Okay, we want bigger size tomatoes, only bigger size tomatoes. Okay, so what we are doing is, for example, let's say if we took a small, let's say we have started with a small one. Okay, so there are 50 tomatoes and we have chosen the smallest one. So now what we should do, we need to take another one. If it is bigger than this, we should discard this and we should keep this. If we take another one, we should discard this and we should keep this. If we take another one, we should discard this and we should keep this. And if after this, like if we take something smaller, we should discard this and we should keep this. Okay, like this, what we should do is, we need to go from worst to best. Okay, we are going from worst to best. So what I'm telling is, if we start with worst, then we need to examine everything, like so it doesn't really help. But if we start with the best moves, like if, for example, let's say let's say there are so many small things, and there is this one and there is this one. If you start with this, we can discard all of this and we could directly go to these things, right? So like that అనమాట. Sorry for my Telugu. Okay, in fact, if your order moves well, alpha beta only needs to examine about, like if you do that, what will be the time complexity? It will be big of b power m by 2. Okay, it will only be it will only become b, it is, and like compared to, like we need to only do this, like comparing to big of b power m. This is smaller, like this is the best thing what we can do, like that's a massive saving. For just the effective branching factors drop from about 35, like from about 35 instead of 6. Let's say in chess, even simple heuristics for move ordering help. For example, we can try capturing moves first, then threads, then forward moves, and finally backward moves. This already gets us close to the theoretical best. We can also use dynamic move ordering. That means learn from the past. For example, if a move worked well in the previous search, try it first again, or use iterative deepening. First search to depth 1, remember the best path, then search to depth 2, but use the remembered path to order moves. So strong moves are often called killer moves, and the technique is called the killer me heuristic. Like for example, like we said, like it will become big of b for m by 2, right? And adding dynamic moves. That's it, that. Okay, and we have another powerful technique in game like chess is the transposition table. Okay, here the idea, sometimes, like two completely different, okay, two completely different sequences of moves can lead to the same position. Okay, with they end up at the same position. Why should we evaluate that position twice? Instead, we save its evaluation the first time in hash table. Like for this we can do, then it will become similar to this only, right? Same, not similar, we can say same. Okay, this is called transposition table. Okay, it can almost double the depth of search we can achieve, but since we may be evaluating millions of moves per second, we can't store them all, so we use strategies to keep the most useful ones and discard the rest. Okay, next topic is imperfect real-time decisions. The Minimax and alphabet algorithms have to search all the way to terminal states for at least a portion of the search space. Now let's face reality. In real games, we don't have unlimited time to search until the terminal states. A chess program can't spend hours thinking about one move. So what do we do? Okay, this depth is usually not possible because moves must be made in reasonable amount of time, typically a few minutes at most. We have two key tricks, like the two tricks are: replace the utility function with a heuristic evaluation function eval. Okay, often it is called as eval. And replace the cutoff test. Okay, replace the terminal test with a cutoff test which decides when to stop. I don't know, maybe you have heard what I said till now or not. Let me just repeat again. Now let's face reality. In real games, we don't have unlimited times to search until the until the search reaches terminal stage. Chess programs doesn't spend thinking about one more unlimited time thinking about all this. So what do? we have two key tricks, like replace the utility function with a heuristic evaluation function, often called eval. Okay, replace the terminal test with cutoff test, that which decides when to apply eval, when to stop searching. Okay, this gives us something called heuristic minimax. Instead of searching until the very end, we stop at depth d. Okay, we stop at depth d and use eval state. Okay, uh, this is the just say this, you will understand. Okay, and evaluation functions for min-max. Okay, an evaluation function estimates the utility of a game state. A good evaluation function is crucial. It must rank states in the same order as the true utility. Okay, win should score higher than draws higher than losses, and it should be fast to compute. In chess, for example, the evaluation function might count the number of pawns, knights, bishops, rooks, and queens for each side. These are called features. Different combinations of features put states into different categories, like 2 pawns versus 1 pawn endgame. Okay. What are the values that are expected in evaluation? Now, not every category guarantees a win or lose. Some lead to wins most of the time, some lose, some to losses, some to draws. For example, if in a certain pawn configuration, 72% of cases lead to a win, that is +1. Okay, 20% of loss, 0 here. 20% of loss, 0, and 8% to draw. Okay, then the expected value is 0.72 plus 1 into 0.20, 0.08 into 1 by 2 equal to 0.76. This gives us a way to assign a single evaluation score even when outcomes vary. Okay, outcomes may change, outcomes may differ, but this gives us a way to assign single evaluation score when outcomes vary. Okay. Most evaluation functions use weighted linear combination of features. Okay, weighted linear combination of features, like for example, let's see this this formula here. Eval of a structure, let's say. Let's talk like this. Okay, here each f of I, here if each f of I, here each f of I is a feature of the state. Okay, and each w of I is a weight. This is a feature of a state and this is a weight. Okay, for chess the features are the number of let's talk about chess here. For chess, for chess the features are in the features are the number of each types of piece. The features are the numbers of each types of piece, and the weights are the relative values, like pawn equals to 1, knight or bishop 3, rook 5, queen 9, etc. Other subtle features like pawn structures or king safety might be worth half a pawn. Are you understanding what I am trying to say here? Okay. Like adding up the values of features, assume the contribution of each feature is independent of the values of each features. Current programs of chess and other games also use non-linear combination of features. The features and weights come from centuries of human chess playing experience or estimated by machine learning techniques. Like, of course, assuming features are independent is not always true. Modern chess programs use nonlinear combination of features. The weights and features can come from centuries of human knowledge, or even better, be learned automatically through machine learning, right? Like we have cutting off search. Next, the alpha beta set should be modified so that it calls a heuristic eval function when it is appropriate to cut off the search. The lines mentioned in terminal test in the program is replaced by if cut test state that then return eval state. Bookkeeping should be done so that the current depth is incremented on each recursive call. If fixed depth limit is so it must also return true for all technical searches. That also helps with move ordering. Okay, coming to the cutoff sets, in practice we use cutoff test. Okay, the alpha beta set is modified, like it is modified to if cutoff test state depth then return eval state. Okay, this means we fix what depth of d. Okay, we have fixed depth d. Beyond that, we stop and use the evaluation function. Okay, when we reach depth D, we stop. Okay, after stopping, we use eval function. The depth is chosen so that the program can move with the time available. Iterative deepening is often used here too, as it helps move ordering. But cutoff search alone can cause big problems. Suppose we stop at a position where a capture is possible. The evaluation might swing wildly in the next move. Such unstable positions are called non-quiescent. Okay, the solution is quiescent search. Okay, the solution is quiescent search. Continue searching beyond the cutoff until the position is stable. In chess, that usually means exploring all capture moves before applying evaluation. Okay, horizon effect. Another tricky issue is the horizon effect. This happens when the algorithm tries to avoid a bad outcome just by pushing it beyond the search horizon. For example, delaying a losing move but not avoiding it. One solution is singular extensions. If a move is clearly better than all others, we allow it to extend the search deeper even beyond the normal depth limit. Okay, and another technique is forward pruning, cutting off some moves immediately. For example, beam search considers only the top n moves at each step, or more advanced prop cut, a probabilistic cut. Instead of pruning nodes that are probably bad, it prunes nodes that are probably bad based on shallow searches and statistics. In fact, ProCut has been shown to best stand at alpha beta 64% of the time, even when alpha beta had more time. Combining all the techniques described here results in a program that can play creditable chess or other games. Like when we combine these techniques, evaluation functions, quiescent sets, transposition table, forward pruning, we can reach around 14 plays deep in chess compared to just 5 plays of raw min-max. That's enough for expert level play. But to reach grandmaster status, we need highly tuned evaluation functions and large databases of opening and end games. Search versus lookup. Speaking of databases, many programs use lookup tables instead of search for opening and end games. For opening, they rely on expert knowledge from books. For end games, computers go beyond humans. Entire end games up to 7 pieces have been completely solved and stored online. That means the program doesn't even search, it just looks up the optimal move. That's what search versus lookup is. Like, many game playing problems use table lookup. Like for opening, the computer is mostly relying on the experts of humans. The best advice of human experts on how to play each opening is copied from books and entered into tables for each computer use. Computers can also gather statistics from databases of previous played games to see which opening sequence most often lead to a win. In early moves, there are few choices and there's much expert commentator and past games on which to draw. Usually, after 10 moves, the program must switch from table lookup to search. Near the end of the game, there are again fewer possible positions and thus more chance to do lookup. Here, the computer has the expertise. Computer analysis of end games goes far beyond anything achieved by humans. The computer can completely solve the end game by producing a policy, which is a mapping from every possible state to the best move in the state. Then we can just look up at the best move rather than recompute it anyway. All chess endgames have been solved up to 7 pieces and are available on the internet. And stochastic games. In real life, many unpredictable external events can put up into unforeseen situations. Many games mirror this unpredictability by including random elements such as throwing of dice. We call this stochastic games. Backgammon is typically a game that combines luck and skill. Dice are rolled at the beginning of the playtime to determine the legal moves. Although white knows what his or her own legal moves are, white does not know what black is going to roll and thus does not know what black's legal moves will be. That means white cannot construct a standard game tree of the sort we saw in chess and tic-tac-toe. A game tree in backgammon must include chance nodes in addition to max and min nodes. Chance nodes, such as the figure, the branches leading from each chance node denote the possible dice rolls. Each branch is labeled with the roll and its probability. There are 36 ways to roll 2 dice, each equal likely. Because 6 to 5 is same as 5 to 6, there are only 21 distinct rolls. The 6 doubles 1 1 through 6 6 each have probability of 1 by 36. Okay, now let's look at the games with chance elements called stochastic games. Chance elements games are called stochastic games. A good example is backgammon, where dice rolls decides the legal moves. This means we need to add a new type of node to the game tree, chance nodes. Each branch from a chance node represents a dice roll with probability attached. For 2 dice, there are 36 outcomes, but only 21 distinct rolls. Okay, what here? 1 1 through 6 6. Okay, each have same probability of 1 by 30. So only we get 21 distinct rolls we get. See, here we see the backgammon tree. Here we have max, min and the new node chance. We have included the chance nodes too. Okay, in this diagram, like a schematic game tree for backgammon, circles represent nodes. Okay, these circles represent nodes. Branches show possible dice rolls. Here they are showing the possible dice rolls. Okay, what rolls can be possible, and our probabilities are labeled like 1 by 36, 1 by 18, like that. The probabilities are mentioned here. And this is the backgammon tree, the schematic game tree for backgammon position. Okay, in schematic games, Minimax is generalized to Expectiminimax value. Like, it is called as Expectiminimax value because we have added the new node like chances. It changes. Okay. Instead of a single min-max value, we calculate the expected value of a position, averaging over all dice rolls variable probability. Like formerly, like we have value of a sum of, okay, P of R into value result S comma R. Okay, R is the dice roll. The complexity is much higher. For min-max, we go off. I couldn't see. Okay. We are not getting there. Okay, like min-max, we cut off. Wait 1 second. Like Minimax, we cut off Minimax too using evaluation functions. But here we must be careful. Scaling evaluation values changes which move looks best. So evaluation must be a positive linear transformation of the probability of winning or expected utility. Okay, like the complexity of expecting minmax, like the complexity is much higher for minmax. For minmax b power m is the complexity. For expecting minmax, big of b power m uh, into n power m, where n number of dice rolled. Okay, in backgammon, let's say n equals to 21, then we get b similar to 20. Sometimes b can be higher, much higher. B can be much higher, as high as 4000 factorial. Okay, so in practice we can only look about 3 piles ahead, only 3 plies ahead. Okay. Alpha beta pruning can still help even with chance nodes, if you have a doubt regarding that, and now we have Monte Carlo simulation. Monte Carlo simulation. One alternative is Monte Carlo rollouts. We can say like the simulation is called a rollout, right? We can call it a Monte Carlo rollouts. Here, instead of expanding the entire tree, the program just plays thousands of random games against itself from the current state using random dice rolls. The win percentage gives a good approximation of the state's value. Even if the heuristic isn't perfect, this technique has been very successful in backgammon and other stochastic games. Okay. And other topics to be investigated in game playing: partially observable games, example Kriegspiel; partially observable chess; card games like bridge, wedged hearts, and some types of poker; state of the art game programs; alternate approach other than Minimax. To wrap up, there are more exciting areas in game playing: partial observable games like poker or platform or blind chess; state of the art programs that combine search, learning, and databases; and alternative approaches beyond Minimax. Game playing has always been a frontier for AI, pushing us to create smarter strategies, better heuristics, and more efficient searches. Okay, that's all. Don't forget to like, comment if you have any doubts, and don't forget to subscribe to my channel. And thank you.